Got it? Ahem. 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 I'll begin. Today, Father, we thank you for this day, and I just pray that you'd help us to understand a little bit more our series and perhaps sequences today as we study. Lord, in your name I pray. Amen. All right, so I'm going to start. I'm going to begin with stating the definition again. So here's a definition. The series with ith term a sub I in the reals, all right, is denoted the sum I equals, well, really you can have whatever you want here. So let me just be a little bit general for a second. N sub naught to infinity, a sub I, right? Which we also use the notation a sub n naught plus a sub n naught plus 1 plus a sub n naught plus 2 plus dot, 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 all right? So this is a series, right? Then we say, and let me just, for the sake of not writing this like a kabillion times, let me call this thing S, all right? So we say S is a summable series, aka a convergent series. Yesterday I used the term convergent. Today I'm going to try out the term summable because I think it might be helpful. It's a summable series if the limit as n goes to infinity of the sum I equals n naught to n of a sub I is equal to L, which is some real number. Furthermore, the nth partial sum of S is S sub n, which is equal to the sum I equals 1, I equals n naught to n of a sub I. Okay. Moreover, if S sub n is, put parentheses on here, a divergent series, listen to me, sequence, then S is not summable, which we could also say, aka it's a divergent series. The reason I'm trying to introduce the terms summable and not summable, or you could say unsummable if you like, is I wanted to draw your attention to the distinction between convergence for a series versus convergence for a sequence. Okay? The convergence for a series you know, the convergence for a series with ith term a sub I is different than the convergence for a sequence with ith term a sub I. Right? I mean, actually, whether or not the series is summable is judged by the convergence of the sequence of partial sums. Let me, again, illustrate this with an example. So we could look at the sequence 1 over n. Well, maybe I guess I should do 1 over I, right? 1 over I equals 1 to infinity, right? The limit, oh, I'm sorry. I did 1 and n. I'll make up my mind eventually, guys. I'm sorry. It doesn't really matter, but 1 over n. Limit as n goes to infinity of 1 over n equals to what? 0, right? Now, in contrast, if I look at the series, yes, it's 0. Series with, say, a sub n equals to 1 over n, right? In other words, I look at the sum, right? N equals 1 to infinity of 1 over n. Yeah.
The sequence of partial sums, then, how many things do we have to take? So, like, how many, like...
all of them.
All of them.
Yes.
Like, to determine if, like, so, like, 4 or 5 or...
It depends on the nature of the example. I mean, generally, we have to consider an arbitrary partial sum in order to figure out what the limit is. So the geometric series that I did at the end of last class, we actually found a formula for S sub n. So it wasn't enough to figure out the second or third or fourth partial sum. In fact, we had to figure out the nth partial sum to take the limit. I mean, that's, yeah. Of course, we are soon developing theorems which will allow us to determine whether or not a series is summable simply by indirect reasoning. So even if we can't actually calculate what its sum is, this L would be its sum, right? If it exists, that would be the sum of the series would be L. L would be the sum of the series. This L, in the case it's summable. Yeah. I will admit, I genuinely, after time goes on, I don't distinguish in my mind between the series and its sum. I mean, if you watch lectures from past years, you'll see me saying that the series is the sum. The difference is the series exists whether or not it's summable. When it's summable, the series can be identified with a real number. When it's not summable, it can't be identified with a real number. So that's the difference. But this one here, this would be what? This is notation for 1 plus 1/2 plus 1/3 plus ... you know? Right, so we would actually have to calculate. I mean, you can look at what is the sequence of partial sums here? Well, it would be S1, right? S2, S3. What are those explicitly? Those are 1, 1 plus 1/2, 1 plus 1/2 plus 1/3, and so forth and so on, right? Which is, you know, 1, 3/2, 6 plus 3 is 9 plus 2 is 11 sixths, I suppose. In fact, you can prove that the limit as n goes to infinity of this Sn is infinity. So the sequence 1 over n converges to 0, but the series with terms 1 over n, right, it is not summable. It diverges. Why? Because the sequence of partial sums diverges. I've not shown that it diverges. I mean, I've given you some kind of, you might believe it, right? You can see what's going to happen here. What happens when I add the fourth? What happens? It gets bigger, right? If we keep adding things, we just keep getting bigger and bigger and bigger and bigger, right? Yeah.
So the top function that we have, that we say that converges, and then we say that the bottom function, I mean the same function, but we say
We must be precise. You say function. So the sequence 1 over n converges to 0 as n goes to infinity, right? So the sequence, this is, I'm saying, that converges to 0, right? This sequence.
Okay. But if it converges, how can it diverge?
It's not the same thing. The series sum n equals 1 to infinity of 1 over n diverges.
Oh, okay.
And it's not because that diverging, this, it doesn't mean, this is not a sequence. The sequence which diverges is this one. It's 1, 1 plus a half, dot, 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 1 plus a half plus a third, plus dot, 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 plus 1 over n, comma, dot, dot, dot. This is the divergent sequence. Right? This divergent sequence, this is the sequence of partial sums for the 1 over n series that diverges. What?
Like why? If it goes to infinity, is it 1 over infinity? Like the sum of that, wouldn't it like be 2 or something?
No.
Like
This
1
this
plus
this
1 half is 1 1/2 plus another half plus a third, right? Like why doesn't that go to 2? Does that make sense? Like just stated it all? No.
I mean that's a temptation to think it does that, but it doesn't. I can prove it. Yeah.
So the sequence converges to 0, but it's a divergent sequence.
It's a divergent series. The series is not summable. This series is here, not summable. Why? Because its sequence of partial sums, this right here, is the sequence of partial sums that diverges. Yeah?
What's that series called? Is that a name?
Sequence of partial sums. Oh, you mean the series? It's the harmonic series. Yeah, yeah. Yes, sir.
All right. So the sequence of 1 over n converges.
Yeah.
The series of 1 over n diverges because the sequence of that series is not summable.
Right.
Yeah.
The sequence corresponding to the series is the sequence of partial sums. Right. And it is not the same as the sequence of the terms in the series itself, obviously. I mean, those are different sequences.
Because it is possible to have a series converge, right?
Oh, yeah. 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 Certainly. Here, let me show you why that. Let me just go ahead and give you the proof while we're on it. We can draw a picture to prove it. And in so doing, we'll discover a test. 1 over x looks like this, right? It's y equals 1 over x. If I wanted to picture the series, the harmonic series, this sum n equals 1 to infinity of 1 over n, what would that look like? Well, I got to choose my choose my picture carefully, I should choose this picture. If we look at it, it's this, right? There's 1. There's 2. My picture's not very good. So this is supposed to be 1, 2, 3, 4, right? So what's this? This is, the area of this is 1. The area of this box, see that my picture's not very good. This should be half. Because if this is 1 over x, this point right here is supposed to be 2 comma 1/2, you know? My picture's not quite to scale. So this should have an area of 1/2. What's the area of this one? Again, my picture's horrible. This is 3 comma 1/3. It's not a 1/4. It's judged. I set it up by the left end point, right? So the area is 1/3, right? And sorry, try to do better. I'm sad. Anyway, I'm trying, guys. My point is, you can picture the series as this stair step, right? Like the value of the series, if it was summable, if the sequence of partial sums did converge to something, it should be represented by that area. Do you guys agree? So, and yet, we could also study the area under the curve, y equals 1 over x, right? We could study this shaded orange region, right? That would be described by the integral from 1 to infinity of dx over x. Yeah.
So if you asked us to prove that on a test, we'd use the integral test and just like kind of be done with it?
We don't know the integral test yet.
Isn't that?
Yes. So this is the limit as t goes to infinity of the integral from 1 to t, right? We did this. And so we get limit as t goes to infinity of, natural log of t minus the natural log of 1, which of course is infinity. So what I've shown you is that the area under the curve y equals 1 over x is infinite. But you can see from the picture that the area represented by the harmonic series is larger than that. So basically by the comparison test, if you like. So by comparison test, the sum n equals 1 to infinity of 1 over n diverges. But Darius is right. I mean, this is an example of what's called the integral test. The integral test is basically just it's this argument I just made done for an arbitrary series. It's also kind of a weapon of last resort. But this is the integral. I'll write it down. Integral test says if we have f of n equals to a sub n, where f of x is continuous, positive, and decreasing on 1 to infinity, then the sum n equals 1 to infinity of a sub n shares the fate of the integral from 1 to infinity of f of x dx. I use some colorful language for the punchline. What I mean by share the fate is if the integral converges, the series is summable. If the integral diverges, the series is not summable. If this converges, that converges. If this diverges, that diverges. That's the integral test. So this gives us what's called the p-series. Application to the p-series. I'm kind of getting out. You guys get me out of order here with your questions. That's okay, though. I'll do it over here. So what is the integral of dx over x to the p equals what? 1 to infinity.
Limit as t goes to infinity, 1 over p.
The integral from 1 to t of x to the minus p, right?
Oh,
Now let's assume that p is not equal to 1. We already know what happens when p is equal to 1, right? P equals to 1 is what we just did on the other board. So let's suppose p is not equal to 1. If p is not equal to 1, then this is what? This is the limit t goes to infinity of what? That's negative p plus 1, right? Divided by minus p plus 1, evaluated from 1 to t. I'm going to clean that up just a bit. So we've got the limit as t goes to infinity of 1 over 1 minus p times, let's say, so x to the 1 minus p is equal to 1 over x to the p minus 1. So with that in mind, this evaluates to 1 over t to the p minus 1 minus 1. So how's that limit work out? There's cases to consider, right? Let's see here. This is equal to, it's going to be equal to 1 over minus 1 over 1 minus p if what? How can I make this go to 0? I just need p what? Greater than or you're right. I want p minus 1 to be greater than 0, which is to say I want p greater than 1. And on the other hand, it's infinity if p is less than 1. Because if p is less than 1, then p minus 1 is negative, which means it's effectively like a positive power of t, which, if it goes to infinity, just blows up. Does that make sense? So in total, of course, we already showed that p equals 1 diverges, right, in my previous calculation. So you put this all together, we can apply, well, let's see, f of x is equal to 1 over x to the p. What can we say about that? Well, let me hide some details here. I'm cheating a bit. Fine, I'll fess up. This is continuous, certainly, right? For x greater than or equal to 1, right? Is it, it's positive, right? Got that too, for x greater than 1. Is it decreasing? Let's see here, df dx is what? That's the easiest way to look at it, right? d dx of, I mean, whatever. Let me just do it. Differentiation right here. So minus p over x to the p plus 1. That's the derivative. And yeah, that's going to be, well, I say that's less than 0, provided what? I mean, this is not necessary, but it's helpful. I'm not thinking about negative x, but more to the point. More to the point. What do we need about p? For that to be negative, we need p what? Right, p positive. Now, certainly, we fall into that case in our first case, right? When the interval converges, when the integral converges f of x equals 1 over x to the p is a positive, continuous, decreasing function, so the integral test applies. And so from this, I can reason that the sum n equals 1 to infinity of 1 over n to the p converges for p greater than 1. It is in fact true that the series diverges, the 1 over n to the p series diverges if p is less than 1, but technically I shouldn't use the integral test to show that because f is not a decreasing function in that case, is it? Let me look this up for just a second, see what your book has to say. I think I have let's see where I've gone to here. I think you guys have roped me into showing you something from the start of section 9.3. We're still not done with 9.2. Theorem 9.10, if f is positive, continuous, and decreasing, they either both converge or diverge. All right, so I did remember it right, if we trust the book. I trust the book on this. I'm currently working out theorem 9.11. So why does it diverge then, you know? So my point is, as much as I'd love to, we actually also, we get diverges from what? With this argument, we can also say that the sum, I don't need to write it again, diverges when? P, all right, for 0 less than p, less than or equal to 1. So all of this from the integral test, except for what? The equal, right? Well, excuse me, equals is the integral test, but the integration's over there. For the rest of it, we're going to need what's called the nth term test. Let me just state that for you. I really need to get back to the geometric series. Where was I? Theorem, so-called nth term test. The sum n equals 1 to infinity of a sub n is summable implies that a sub n goes to 0 as n goes to infinity. Here's another way to say it. In other words, if a sub n does not go to 0 as n goes to infinity, then the series n equals 1 to infinity of a sub n diverges. Really, the second sentence, this piece right here, is what we usually think of as the nth term test, okay? You have to be careful. This is an implication. It's an if-then thing. It does not go both ways. We've already seen that. Example 1, the harmonic series. The nth term is 1 over n. It goes to 0. And yet, that series is not summable, right? It diverged. Mm-hmm.
It goes to some other constant that is, goes to some other constant and still diverges, right?
What's that? Say again?
So if a sub n does not approach or go to 0 as n goes to infinity, what if it goes to like 5 or 3?
3. You want 3?
If it does go there, doesn't it still mean that diverges because it's not going to 0?
Yes, this is what the test says. It says if it goes to something other than 0, it diverges. What it does not tell you is that if it goes to 0, it converges. If it goes to 0, great. That's nice. It might converge. It might not. Like this one, diverges. It's not summable. Why? Since inverse tangent of n goes to pi over 2 as n goes to infinity, right? Thus, this series, when in sum n equals 1 to infinity of inverse tangent of n, diverges by nth term test. So nth term test is only useful for, it's like a no-go theorem. If the nth term in the series doesn't go to 0, well, game over. The series diverges. If the nth term does go to 0, it's nice, but it doesn't prove anything. It just proves you need to consult other tests. Now over here, let me do my example 4 over here. See, if we look at the sum n equals 1 to infinity of 1 over n to the p, where, what's the case we want to look at? How about p being p is okay, so integral tests got us all this, right? So what should we consider? What is left to consider? P, so the case which is still left over, the case which is pending, so to speak. So you should consider p less than or equal to 0 by some other method, right? And that's what my example 4 is in the process of doing. So let's think about p less than or equal to 0. We can take care of that case for the p series using this nth term test. If p is less than or equal to 0, right, then notice that minus p is greater than or equal to 0, right? Agree? So if we look at 1 over n to the p, which is my a sub n, well, that's equal to n to the minus p, right? And so we've got n to the minus p. Minus p is a positive power, right? What happens is this goes to infinity. As n goes to infinity, this goes to infinity, or what? So let's say p not equal to 0. P not equal to 0, this goes to what? This goes to infinity, right? As n goes to infinity. And of course, p equals to 0 was my first example, actually. See, because p equals to 0 is the sum n equals 1 to infinity of 1 over n to the 0, which is also known as the sum n equals 1 to infinity of 1, which diverges because, well, I actually proved that directly. I showed you that the nth partial sum of that was n, and we noticed that that went to infinity last class. So that diverges. Or if you like, nth term test, right? So here a sub n equals to 1, which of course does not go to 0 as n goes to infinity. So what these results I'm trying to gather together for you right now, we collectively refer to these as the p term, as the p series result, or the p series theorem, or we just say it's a p series with p equal to blah. And here's the big thing to remember. Here it is in its glory. Sum n equals 1 to infinity of 1 over n to the p is, I'll just write it as a case-wise thing, equals convergent for p greater than 1, and it's divergent for p less than or equal to 1. This is the so-called P series. The P equals 1 series is the harmonic series, my example 1 from today. Okay? Now you got to be careful with the nth term test. It's helpful, but be careful how you use it. Make sure you're actually looking at the nth term. Here's one. Sum n equals 1 to infinity of, say, inverse tangent of n plus 2 minus the inverse tangent of n. If you are careless, you might go, oh, inverse tangent goes to pi over 2, so by nth term test, this diverges. Right? That would be careless because the nth term is not just inverse tangent, right? The nth term is what? This whole thing, right? And what happens, this goes to what? This goes to actually pi over 2 minus pi over 2, which is equal to 0, as n goes to infinity. Thus, nth term test, inconclusive. It gives you no information. All right? Yeah.
Is there an order, and like, so like, in that case, if the nth term test is inconclusive, is there a smart way to go about which test to use? Because you said the integral test should be more of a last resort.
Yeah, I would not do the integral test just yet, but yeah. I'm about to show you. So this one, actually, anytime you have something that looks like this, it looks like something fairly similar, and the difference of those things, it's probably a telescoping series. This is what's called a telescoping series. I'll show you why. So we calculate the nth partial term, the nth partial sum of this series. So that's what? Inverse tangent of 3 minus inverse tangent of, let's see here, n equals 1 gave me 3, 1, right? That's n equals 1. Then n equals 2 is what? N equals 2, yeah. Let's see here, n equals 3. All right. N equals 4. 4 plus 2 is 6. All right, let me just try to make sure we understand what I'm doing. This is n equals 1. This is n equals 2, right? I mean, this is n equals 3. This is, I mean, technically it's A4, right? That's A1, that's A2, this is A3, that's A4, all right? I'm just writing them down. And then we keep going. And eventually we get to the last couple terms in the words, partial sum. So let's look at inverse tangent of, let's say, n minus 3 plus 2 minus the inverse tangent of n minus 3 plus the inverse tangent of n minus 2 plus 2 minus the inverse tangent of n minus 2. I think I wrote too much here, guys. I'm sorry. Inverse tangent of n minus 1 plus 2 minus the inverse tangent of n minus 1. Man, I'm a glutton for punishment here. All right. I don't think you need to quite write this much, but it probably is not bad. All right, there it is in all of its glory. So what I'm attempting to write down here for you is the nth partial sum. What happens? Telescopes, yeah. So check it out. This tangent 3 cancels with that minus tangent 3. This tangent 4 cancels with that inverse tangent, right? And there's an inverse tangent of 5 subtracted in the next term I didn't write down, right? So this cancels as well. What's left over? What's not canceled? Right, this guy and this guy are not canceled by anything in the partial sum. This one's also canceled by something I haven't written. And then when you get to the other tail of it, this inverse tangent of n, is there a tangent? Oh, that's right here, right? Minus 2 plus 2. This cancels that, right? And this is actually canceling this one, right? I'll put a Pac-Man on it. So you can tell which one was which. What else here? And I guess you can see that these are going to be canceled by things that are in the middle, right? So what's left over? These two things, right? So let me collect the thought. We have just shown that S sub n is equal to inverse tangent of, what we got here, n plus 2 plus inverse tangent of n plus 1, right? Minus what? What would you say?
Minus inverse tangent 1 minus inverse tangent 2.
All right, very good. So we can go back to the definition of series, right? The series is summable if its sequence of partial sums converges. Again, here, we actually could calculate the sequence of partial sums nth term. This is, again, a precious, rare, and wonderful thing. It doesn't usually happen, but for a telescoping series, it does. And so this one, we can see that Sn goes to pi over 2 plus pi over 2 minus pi over 4 minus the inverse tangent of 2, which I don't happen to know off the top of my head. Any of you guys know it? That might be something pretty. I don't know. Oh, you find it for me? All right. You phoned an electronic friend. I'll allow it. Let's see here. So that's pi minus pi over 4. That's 3. Looks like we got 3 pi over 4 minus the inverse tangent of 2, which we're still up in the air. What is that? 63 degrees? Yeah. I need radians. Yeah, we work in radians. It came from physics? Yeah, people give me angles in radians. I get mad in physics. No. 1.11. All right, well. Trying to think what that would be exactly. I don't know, but there's an approximation. So the series converges to this. This is the sum of the series. I probably should say this is the sum of the series. Be a good math professor. This is an approximation to the sum. Yeah.
So how could you tell that the inverse tangent of n plus 2, those terms went to pi over 2?
The inverse tangent tends to pi over 2 as n goes to infinity. N 2 plus infinity, still infinity. So if I shift n, it doesn't change the limit. I could have inverse tangent of n to the 5th plus n to the 4th plus 3n plus 17, and it would still go to pi over 2 as n goes to infinity because, yeah. As long as the thing going into the inverse tangent is getting huge, goes to pi over 2. Yeah. That's a telescoping series. There's no, let's say, test for telescoping series. It is, you just kind of have to see them for what they are. And sometimes they're hidden. There are telescoping series which require you to do partial fractions before you can actually see the telescoping. There are examples like that out there. For example, number Am I looking in your book for a problem? I'm doing that, aren't I? Maybe it's in 9.2. Excuse me. Number 19 and number 20. But your book, as usual being insulting, has told you to use partial fractions on these problems. How dare they? So this one, sum n equals 1 to infinity, 1 over n times n plus 1. Yeah. So if we look at 1 over n times n plus 1, that would be a over n plus b over n plus 1, which is 1 is a times n plus 1 plus b times n. So you can see, let's see here, put n equals to 0 gives me 1 equals to a. If I put n equals to minus 1, I can see 1 equals to minus b. So you see this is the sum, n equals 1 to infinity, of 1 over n minus 1 over n plus 1, which you might be tempted to think, guilt by association, you might think, well, that diverges, right? We just saw that example 1 today. 1 over n blows up. But no, this one actually converges. Because it's not 1 over n. It's related to 1 over n, but it's not the same. You have to be precise here. It's so important to be precise. You can't go off fuzzy notions. If you go off fuzzy notions, you'll just be wrong. Sad but true. So the nth partial sum, the sum, let's say j equals 1 to n of 1 over j minus 1 over j plus 1, right? What is that actually here? So we got 1 minus a half plus 1/2 minus a third plus a third minus a fourth plus plus, and here I'll look at the n minus 1th and n minus, here's the n minus 1 term, this can be the nth term. So n minus 1, I get 1 over n minus 1 minus 1 over n, and then finally 1 over n minus 1 over n plus 1. If I was smarter, I would have led with this example. Oh well, by now you guys know I'm not that smart. So this is number 19 in your textbook, by the way. This is number 19 from section 9.2. So we got all that survives is this guy and this guy. Let's see here. So in total, the nth partial sum works out to 1 minus 1 over n plus 1, right? And you can see that this goes to 1 as n goes to infinity. So thus, the sum, n equals 1 to infinity of 1 over n times n plus 1 is equal to 1. Which is really kind of cool, by the way. If you look at what that means, I mean, what is that? Some n equals 1 to infinity, 1 over n times n plus 1. What is that, actually? It's put in 1, you get what? 1 times, it's a half. The first thing is a half, right? Oh, I just worked it out over here, didn't I? So that's a half. What's this? It's a sixth, yeah. But it's easier from this formula. Right? N equals 3. 3 times 4. 12, yeah. N equals 4. 4 times 5. 20th, yeah. Yeah, I mean, obviously this is equal to 1, right? I don't think that's obvious at all. Right? It might be more obvious if you actually got into the decimals. You can kind of see things getting closer to 1 if you look at it and study it, right? But we proved it here. What other tests are there? See, all right, so where are we going? What are we doing? Our goal is to understand series. We want to understand when are they summable, when are they not summable. Given a particular series, you want to be able to answer the question, does it converge or diverge? That's the question we're focusing on here for a little bit. We have just a few weapons in our arsenal at the moment. If it happens to be a p-series, we just look at the value, and if it's greater than 1, it's convergent. If it's less than or equal to 1, it's divergent, right? So that's a whole family of examples we know. We can do the integral test if we want, right? We can look and see if it's telescoping. That's another way. We can use the nth term test if we think it doesn't converge. Maybe the nth term test will reveal it to us, right? But the nth term test is not universal in terms of detecting divergence, right? Nth term test fails to reveal the harmonic series is bad. It diverges, right? So we need more tests. We need more tests. So one of the next tests that's out there for you guys I still need to go back and talk about the geometric series more. Our comparison tests. Now, there are two comparison tests. There's the direct comparison test, and there's also the limit comparison test. Direct comparison is very natural and not that surprising, really. Direct comparison test. I bet you guys could have come up with this test yourself if I just asked you to invent one, and if you hadn't had Calculus 2 before even, although it's hard to, short of some illegal medical technology, which I currently don't have access to, I can't make you forget your previous coursework. So direct comparison is something like this. If A sub n is less than or equal to B sub n, and the sum of A sub n diverges, then the sum of B sub n does what? So what did you say? For case 1? Yeah, also my knee hurts. So what do you say? Somebody said something. So this one would be what? Let's try to put it in words. I'm saying that the sum of this series blows up. It diverges. Right? This is something larger than that. So it must diverge, yeah. This one, suppose the series with larger terms converges, right? Then a corresponding series with smaller terms must also converge. Now, for you math majors, why is this theorem as stated false? There's a very important thing we need here. Otherwise, this isn't kosher. I mean, it's just not true. We need this. This is actually for series with non-negative terms. All of our thinking was based on 0, not allowing them to escape below. You see, if it I mean, it could be that it converges to 0 in this case if it was a negative series or something. But anyway, so that's the direct comparison test. Let's see if we can do an example. What example am I on anyway? I lost track. Example 8? 7? Where am I? Example 6? Let's see here. How about the sum n equals 1 to infinity of one over n minus pi. So notice that 1 over n minus pi, right, is less than 1 over n, isn't it?
Yeah.
Now, can I apply the direct comparison test to this series? Not quite yet. Not quite yet, right? Because it doesn't satisfy my criteria for a series with non-negative terms. Like, what are the first few terms in this series? It's what? It's 1 over 1 minus pi, right? Plus 1 over 2 minus pi, plus 1 over 3 minus pi. Now, the next term, 4 minus pi, is actually positive, right? So if I peel off these first 3 kind of oddball terms, then you see I've got then what I have there is a series with positive terms, right? And I have this, right? And more to the point, I have 0 is less than that for n greater than or equal to 4, right? How about this? I also know that the sum n equals 1 to infinity, 1 over n, is what? It's 1 plus a half plus a third, right? Plus the sum n equals 1 to infinity, 1 over n.